You're listening to The Local Maximum, episode 249.
Time to expand your perspective. Welcome to The Local Maximum. Now, here's your host, Max Sklar.
Welcome, everyone. Welcome. You have reached another Local Maximum. Just working the soundboard here. Of course, I'm joined by Aaron today. How you doing, Aaron?
I am doing well. Greetings, listeners.
Yeah, and okay, this is going to be actually a very intellectually stimulating show today. So, are you excited to get started? You're gonna have to wrap your head around some big ideas today. I think. So
well, I have not done my homework, so we'll see how I perform.
No. Well, as I was telling you before, the point of the Local Maximum is not for us to do the research necessary to write a whole grad school thesis and present it on the Local Maximum, but the Sleeping Beauty problem, for example, that we're going to talk about today. It's let's have our initial discussion on it. Let's go a little deep. Let's see what we're thinking about.
As an aside, though, if any of you listeners out there have just written a graduate thesis on something interesting, let us know.
Oh, sure.
That might make for an interesting episode.
Sure. Okay, before we get started on the Sleeping Beauty problem, I want to announce that. So I have never done a debate before in my life. I said that when I had Gene Epstein on the podcast, and he runs the Soho Forum debates, and I told him I've never done it. Well, I finally got roped into doing it.
Not by Gene.
No, not by Gene. It's a minor debate series. It's like a minor leagues kind of a rec sort of.
You're on the New Hampshire farm team.
I guess so.
If you make it big, you'll get called up to Soho.
I don't know. So anyway, the debate is debating against the resolution, monarchy is better than democracy. And monarchy is better than representative democracy. And I feel like there's a lot of people I talk to who have never heard this before. And they're like, oh, you're going to have an easy time. It's so easy. But, they're going to come with some pretty serious arguments, and I have to be prepared. And it's a little harrowing.
Yeah. I mean, I can't claim to have read, many of Curtis Yarvin's writings, but there is a large volume of material written on the subject in favor of the monarchist viewpoint. So it's not like they're going to be grasping at straws, and all they have is
King
literature from the age of kings.
Bend the knee. I feel like he's going to wear his crown and he's going to be like, bend the knee. Do not. I think one of my things should be like, well, if you agree with me, then vote at the end. If you don't, you shouldn't vote because you don't believe in democracy anymore. So that could be a strategy. But anyway, this will be on when. So for those of you who are in New Hampshire, I know it's probably not a lot of you, but this will be in Rollinsford, New Hampshire, at the Shell on Wednesday, October 26th. 6:30 to 9. So if you want to show up for that,
and no tickets required.
No, I don't think so. I don't think any tickets are required. Yeah, you could just show up. If you can get your butt up to Rollinsford, New Hampshire, you can see how I do, for better or for worse.
Now, has a official drinking game been announced? Like, is there a secret word that whenever one of the debaters utters it, we have to take a drink?
I don't know. What would my word be? I know there are definitely words that I say a lot.
Democracy would be too frequent.
Easy.
Yeah, it needs to be a little bit more obscure than that.
Given how I know, I think it's going to be time preference. I think that's what it's going to be.
You know your audience.
Yeah. No. Well, I know how the debate goes sometimes, and no, people have definitely, even if you think you're for democracy, people have definitely over the last few weeks have presented me with things like, oh, I think I can answer that, but I don't, not really off the cuff. So I feel like
it is a deceptively simple seeming question.
Yeah. Well, those are good questions. I think it's going to. So at first I was dreading it. Now I'm excited about it.
I don't. Oh,
and by the way, it'll be with Alu Axelman, who was on the Local Maximum.
Oh, yeah, very cool.
I mean, he was a little. One of the things I disagreed with him was he called the governor of New Hampshire a dictator. So now I'm like, well, don't you think that's good now?
Gonna make him eat his words?
No. I don't know. Maybe.
So you mentioned bending the knee, and a little peek behind the scenes here.
Okay.
After we record this episode, we will be watching the season finale of House of the Dragon.
Yes.
So there are obviously many advocates for the monarchy in that show, in that world, but I'm failing to come up with anyone who is an advocate for democracy,
Right.
or even representative democracy.
No, in Game of Thrones, in the last episode, which I admit wasn't very good, but Sam suggested a representative
That's
democracy.
right. And then everybody paused and then broke into laughter.
Right. But it's also kind of hinted at that the Night's Watch was something of a democracy because they did have elections there.
And when in doubt, you can always just murder your elected representative and start over.
Right. I mean,
That
I
was
feel like I
perhaps
have
not a recurring or a frequent occurrence on the Night's Watch.
Yeah.
Anyway,
Okay. Yeah. Well, if any of you are there's only like 3 days between when we release this and the debate, but if anyone has any ideas for me, please let me know. localmaxradio@gmail.com. I'll be reading that at the last minute. But today, I want to get into the main event for today as soon as possible, and that is as soon as possible, 6 minutes into the show, and that is the Sleeping Beauty problem. Now, this was a problem that's presented as a probability problem that was put to me by AJ Jacobs, the Puzzler, episode 246, and that was actually I had never heard it before, and I was surprised that I'd never heard it before, but it really is a head scratcher because it's really a philosophical what is life problem that looks like a probability problem. And we'll get to that in a bit. So I'm going to state the problem, and maybe we could go a little bit deeper into why it's controversial and maybe give some of our thoughts on it and go a little deeper than I could in that episode. So here's the problem. Here's the rules, okay? Sleeping Beauty is in this experiment. And I don't know why they chose Sleeping Beauty. I don't know why they didn't choose one of the dwarves or Cinderella or whatever, maybe because she sleeps. So she's in the experiment. She knows the rules at the beginning. So I'm thinking of that scene from Airplane when he's like, they bought their tickets. They knew what they were getting into. It's kind of like that. And what the rules are, there's a coin flip. Okay. And then she's put to sleep. And if the coin had landed on heads, she's woken up Monday and put back to sleep. And then if the coins lands on tails, she's woken up Monday and put back to sleep. So she's woken up Monday either way. And then again, she's woken up Tuesday, put back to sleep. And then Wednesday, she's finally woken up for good and the experiment ends. Now.
So before we go
Yes.
on, I don't think it matters.
Yeah.
But it sounded like the coin flip happened before she was put to sleep the first time.
No, yes. And it might matter. So yes, it might matter. That's the key. I don't think it matters, but then when that's not obvious to everyone. And by the way, if I'm explaining this too fast, let me know.
My initial read
so-
had assumed that she goes to sleep and then they flip the coin, but like I said, I'm not sure that it makes a difference.
It might not. It might not. So right. Okay. So here's the thing. Every time she wakes up and is put back to sleep, her memory is wiped when she puts back to sleep. So if it comes up on tails, and so when she wakes up on Wednesday, all she's going to remember is being put to sleep Sunday night. She's not going to remember any of the awakenings. And if it's tails, when she wakes up on Tuesday, she's not going to remember Monday. Okay. If you want to know where this is going philosophically, there's something of a reincarnation theme, I believe, is what's popping up here. So the question is, Sleeping Beauty knows the experiment. When she is woken up, what is her correct credence or probability of heads versus tails on which game she is in?
So she doesn't have to. We're not asking to determine what day is it.
Yeah,
because when she wakes up, it could be Monday, Tuesday, or Wednesday.
Well, no. Wednesday she's told, so she doesn't have any. There's no period where it's So it's really only Monday or Tuesday, and that is also an open question. That's.
But
the
the initial question is simply what do you think the coin flip result was?
Right. But I think the probability of Monday versus Tuesday is very relevant to the problem.
Sure.
So okay, so in that question. That was first put to me kind of live on the spot. I had been reading the book, the Puzzler, a little bit by A.J. Jacobs, and so I had kind of prepared a little bit beforehand to discuss the problem, but I didn't have a lot of time to think too deeply about it. So I was kind of in the majority when they first start thinking about it, which is the thirder position, which is like, okay, when she is woken up, she should say, well, there are two possible worlds, and in world one, I get woken up once, and in world two, I get woken up twice. So there's three possible times that I get woken up. So a third of those times I'm woken up, and it's the heads, and you're drawing like a little tree diagram. Yep. You might want to hold that up to the camera, although I don't think people can see.
I think it's a little too small, but I'm drawing a branching tree, and so the decision is the coin flip,
right?
And then from that, one branch has a single point, which is the only wake them up on Monday,
right? And
the other branch has Monday followed by Tuesday,
right? So there are three possible times to get woken up. Are they all equally likely? Well, I guess we could say they are equally likely because she has no information other than she's being woken up. So she should say 1/3. And maybe there's 1/3 chance of heads, 2/3 chance of tails. And likewise, it would also be a 2/3 chance of Monday and a 1/3 chance of Tuesday. So to put it all together, 1/3 chance heads Monday, 1/3 chance tails Monday, 1/3 chance tails Tuesday. And that's kind of the thirder position.
And so you can immediately see how this might relate back to Monty Hall, because there's some possibly counterintuitive stuff going on here. We're not sure, but there are three possible outcomes, and you're trying to determine which is the. I guess unlike we're not trying to determine which the prize is behind, but which set are we currently in?
I think the difference, it looks like the Monty Hall problem, but the difference between this problem and Monty Hall is that Monty Hall has a very well specified payoff at the end.
Well, not only that, is that in Monty Hall, the all-knowing experimenter or is providing you with additional true information,
right,
at some interval here, and we're not getting all the information we have is that the coin was flipped and we are now awake.
Right. But I want to come back to what I was saying about having like a true payoff, because there was another version of this problem, and I'm not going to get into it in too much detail, that one of these papers come out where there's like, okay, you're woken up and there's 2 jars of jelly beans, and the jars of jelly beans are A and B, but they have different proportions of poison depending on whether it was heads or tails. And you got to, every time you wake up, you have to take a bean out, and then at the end you eat all the beans and you might die. Now, if the problem is formulated in that way, then I could do all my mathematics, I could do all my probability theory, I could do all my algebra, and I could minimize my my probability of dying. And I think that would not pose any problem to me. The problem is there is no kind of payoff here. And so I think the main question is,
other than the satisfaction of being right.
Other than the satisfaction of being right, of course, you're of being right when you're predicting 1/2, 1/3 is not really so much. I mean, the question is, do you get, like, if you're wrong, if the coin lands on tails and you're wrong twice, now wrong is kind of a, you're already predicting 2/3 or 1/2. So, but let's say you're guessing, right? And if you're wrong twice, is that considered worse than being wrong once? You know what I mean? So in other words, is it graded on a curve where like you're graded on your possible Monday responses and graded on your possible Tuesday responses, or are they graded per awakening? Because if they're graded per awakening, then I think you have to take the thirder position where, in Tuesday you're awakened twice. And, what would happen is, let's say I give 2/3 for Tuesday, and I am correct twice, right? So my probability, and the probability that I put on Tuesday both times would have been 4/9. And then on Monday it would have been 2/3. I don't know. That's really interesting. Yeah, if I say Monday, no, it would be a third. I think that's the way to minimize log likelihood loss. I think that's the way to like minimize your expected your expected loss. Whereas the way to score something in log likelihood loss is I give a probability, and then you take the minus log of that probability, and that's your like loss score. And it's bad to get lost. It's like golf rules. So if I gave a probability of something of 1, that's certainty, then I get 0 loss because it happened. But if I have a very small number on it, then I get a very high loss. So that's one way to score. That's one way to score a game where you're giving probabilities. It's a good way.
I believe Metaculus uses a system at least similar to that, if not exactly that.
Yeah. Yes. But the problem is that are you like I'm just multiplying Tuesday's scores together, like I'm giving 2 probabilities, but maybe not. Maybe I kind of average them together somehow. And so then the halfer position would be right if that's how it's scored. If it's like, well, what's your average loss? And so if you're talking about average loss on Monday versus average loss on Tuesday, then I think you're going to have to say 1/2.
I certainly find the halfer position appealing. But I think that may be, at least in part, due to just the fact that that's the way I drew it out first.
So let me...
and so I'm anchoring on my first intuition.
Right. So my first intuition was thirder, but let me give more detail on the halfer position that I didn't give before. So this is from... I'm going to post a few articles on localmaxradio.com/249. And these are on and some of these are halfer position papers. David Lewis and Phil Sci Archive. What is this one? The halfers are right in the end. Who wrote this? Anyway, it's
now is this
by Min Seong Kim, I think. Okay, so
is this as controversial among mathematicians as the Monty Hall problem was at the time that it was it first went broadly public?
Except there's less of a resolution to this one. So the halfer position.
You mean nobody's running this experimentally?
No, I don't think you can.
I think there could be a funding opportunity there.
Yes, but even if you did run it experimentally, and even if the person did give answers, how would you know? There's no experiment you could set up where you'd know, okay, well, they did the right thing or not. You really can't. Again, it's how they score them. Like I was saying before. So if I'm told how Sleeping Beauty is going to be scored at the end, whether it's poison you might die or just a numerical score, which I think if it's Sleeping Beauty I would prefer, then
or a cash reward.
Then no matter what the scoring system is, I could tell you how to either maximize your rewards or somehow maximize your expected utility or whatever it is you want to maximize. I could do the math and do that, but without that, there's really no way of doing that.
So you were going to introduce a piece of information here, but once we've done that, remind me to introduce my concept for risk reward.
Okay, so the halfer position is Sleeping Beauty before she's put to sleep on Sunday thinks it's 1/2 heads and 1/2 tails.
Which seems reasonable. She
receives no new information that she had at the beginning. The only new information is that she is being woken up at least once, but that is true.
Which again is the key difference between this and one of the 2 key differences between this and Monty Hall, that no new information is being provided.
Right. So there's an open question as to whether that is new information. She is being awakened. Well, she knew going into it that there was a 100% chance of her being awakened.
And if she wasn't, she wouldn't be able to process that as new information.
Well, yeah, okay, but we're not. Let's not break out of the assumption
outside the bounds of the
right
parameters.
So she knows that So the thirders will say, but the information is that she is now in the game. But you have the halfers will say you had guaranteed an awakening at the start of the experiment. So then there's really no new information, is there? So it should still be a half. And then obviously for both the thirders and the halfers, when she wakes up on Wednesday, and it's the final awakening, they say it's Wednesday, then she reverts to a half or stays at a half. So the halfers kind of sound like, there's a little bit more, there's a little bit more information. Now they're starting to sound like, okay, maybe they're a little bit more reasonable. So there's a bunch of half positions here. That's certainly not. It's certainly not set in stone yet or resolved. But I do want to say more things. You say your thing.
Yeah, so in terms of kind of the risk reward equation, one of the things, and I wasn't thinking of it in that term, but when it was initially explained to me, I don't think I realized that you only flip the coin once at the beginning. I thought it was a scenario where they get woken up and asked, okay, what do you think the coin flip was? And then either depending on whether they got the answer right or not, or depending on what the initial coin flip was, they flip the coin again. And so you could, rather than the options being you get woken up on Monday or Monday and Tuesday, that you could get put to sleep for a longer and longer and indeterminate time. So there wouldn't necessarily be a guarantee that you exit on Wednesday, that you could be in a scenario where, and if you want to make it a risk reward thing, that wrong answers result in you being put to sleep again.
I see. So in other words, like if it's heads, then you get woken up permanently the next time. And then if it's tails, then you continue and you have to say like, which number awakening is this?
Or maybe that the first flip determines whether you're going to get one, whether you're going to get, whether this will, I guess it's a combination of that there are two ways to exit the experiment. Is the coin flip can give you an exit, or if you call the flip correctly, can give you an exit. I'd have to think more on this, but
also notice she's not calling it; she's just giving probabilities.
Right.
So yeah, it's. I'm not entirely sure where you're going with that. Do you mean
I just thought it was a much darker experiment.
Oh, I see.
In that you could end up kind of stuck in an infinite loop where you keep getting put to sleep and woken back up again, but either by virtue of an extremely low probability event of a dozen heads in a row or something, that you could be put back to sleep and woken up iterative times rather than just the one or two in the base case of the experiment.
Okay, so I'm just going to get through a couple more things. I mean, my question is probability fundamentally broken then? I don't think it is, but I think we have to ask, well, what was probability designed for in the first place? Like, there's frequentist probability, which is you're repeating an experiment many times, which clearly doesn't apply here. And then there is, because one of the very important things that you need to have for a frequentist view of probability is you need to have memory. If you don't have memory, then repeating an experiment multiple times and tallying the result is no good, or is a non-starter. And then there's belief. And belief is a really interesting thing. We've talked about probability as belief for a long time. You kind of think, well, if I put my probability 1/3 here and 2/3 here, I sort of think like, okay, maybe God does play dice. Maybe maybe there's a third chance I'll be in this world and a 2/3 chance I'll be in this world. But ultimately, those beliefs are formed in order to deal with uncertainty about the future. And in this case, there's no like future decision. So we kind of lose our frame of reference when it comes to subjective probability.
Right. To what you said about memory, you can't really apply a Bayesian approach to this because you don't get to take your posteriors and make them the priors to a new assessment.
Well, so a thirder would say, yes, once you know that you're in the game, then that is information that you're in the game. And from that point of view, because there are 3 points, the point of view of being in the game is that there are 3 points in the game that I could be at, and there's a 1/3 chance of each one. So once I get the information that I'm in the game, I'm 1/3. But once I get the information that I'm outside the game, I'm 1/2, which is really interesting. So maybe probability could have a relativistic aspect. I talk about probability as like, okay, relative probability as like probability A is twice as likely as B. But maybe we could put different probabilities on the same event because we are somehow in a different quantum state.
So is this Schrodinger's Sleeping Beauty?
It could be. So anyway, a few more points I want to bring up on this, and unless you have more to say about that, but that is an interesting point. Nick Bostrom adds this, which is obviously a good thing to think about. If you think you're right, you definitely have to, whatever you are, if you think you're right, you definitely have to take this into account. What if Sleeping Beauty is woken up 1 million times in Tails instead of 2? Should she still say 1/2? And obviously the thirders would then change to, 1 million over 1,000,001. And 1 out of 1,000,001. So again, if we say 1/2, then we're wrong a lot more times, than, or we have a greater loss. But if still the same argument holds, like if the loss of all of them are added together, then, or averaged together, then then you're still at 1/2. So that's an interesting question. I kind of added another formulation, which I might not be the first one to come up with, but I have one before. What do you think about that? If you just increase, because on Monty Hall problem, it becomes way more obvious when you increase it to 1 million doors.
Okay, so here's a twist that maybe fits my previous idea a little bit better into that slot. Okay. Is that rather than just flipping a coin, we do two things before we run the experiment, or once we put Sleeping Beauty to sleep the first time. We flip the coin, and we run a random number generator.
Okay.
And if
you keep changing the problem,
if the coin comes up heads,
okay,
then Sleeping Beauty gets woken once and then exits the experiment.
Okay.
If it comes up tails, Sleeping Beauty gets woken up the number of times that came up on the random number generator.
Okay.
Then what do we do?
Well, then maybe you could use the well, first of all, if you're a halfer, it doesn't matter.
Right.
It's still 1/2. If you are a thirder, then you would have to average the distribution of the random number generator, I would say.
If we were ready to transition to the distribution of the week, that would have been a perfect segue. But I don't think we're ready for that quite yet.
Well, this is a crazy story, and the distribution of the week is also a crazy story. So buckle up, folks. Another related thought: what if you learn that it is Monday in this experiment? Right, because you're going to be woken up Monday no matter what. But it does seem like if you wake up and you're a thirder and you're being told, "Oh, this is Monday," it seems like your probability should revert to 1/2.
Yes, because if we're talking about whether it was heads or tails, then we know it's Monday, and we know that there are two scenarios in which we arrive at Monday. So that seems compelling. I'm worrying that there's a trap there that I'm missing, though.
Well, the trap is then you have to be like, okay, well, let's say I'm not told what's the probability that it's Monday versus the probability that it's Tuesday, and if you're a halfer, then you would almost have to say, well, I'm being woken up, but there's a greater chance that it's Monday than Tuesday. And whereas if you're a thirder, if you're a thirder, you're going to say that there's a 2/3 chance it's Monday and a 1/3 chance that it's Tuesday. If you are a halfer, then you are going to have to say, well, there's a 50% chance it's on tails. Given that it's tails, there's a 50% chance that it's Monday. But given that it's heads, there's a 100% chance that it's Monday. Therefore, if I'm woken up, I would have to say it's 75% chance. No, am I right on that? Did I screw that up? Go.
I need the white. Wait. So
you're the one with the piece of paper here. Okay. Oh, no. Let me do this again. Let me go step by step.
Okay.
So if you are I think the thirder position is easier with this analysis because you basically put a third of the weight on all of the 3 awakenings.
Right.
And 2 of those awakenings are Monday. So
Correct.
you would say 2/3 chance that it is Monday, right? Okay.
Yes.
So let's say you're a halfer, okay? You wake up and you say, well, there's a 1/2 chance that it was landing on heads. Given that it landed on heads, there's a 100% chance that it's Monday.
Right. So net 50% for
Monday.
heads Monday.
Right. For Tuesday, there's a 50% chance that it's Tuesday. And given that, 50% chance that it's tails. Given that it's tails, Monday, Tuesday, 50-50. We don't know. So there's another net 25% to
Right.
Monday.
So 50% heads Monday, 25% tails Monday.
Right.
So we renormalize that, and it becomes 2/3 heads Monday, 1/3
No.
tails Monday, right?
No.
Well, because if we know it's
No.
one of those two.
Sorry. No. That's not good. If you're a halfer, you put 75% chance on Monday and 25% chance on Tuesday. The 25% for Tuesday is the half that it's tails, and of the tails, half of that is Tuesday.
Yes. Well, I thought the question was, we've been told it's Monday, and
No,
if we're
no.
a halfer,
You have not been told.
Oh, okay.
I'm
see.
just saying, I'm taking a step back. I'm saying you haven't been told yet, but now you're like, okay, well, given that we're told, we can figure things out. So now take a step back, and what's my prior that it's Monday versus Tuesday? And the halfer versus thirder gives very different credences.
Right.
on
Right.
this.
Yeah. So a halfer will believe at any given time that they're woken up that it's a 75% chance it's a Monday,
Right.
25% chance it's a Tuesday. Yeah,
Right,
that drops out of my diagram. That makes sense to me.
Okay, perfect. I'm glad we cleared that up. So, does that make sense if you are a halfer? I mean, then if you're a halfer in the million door scenario, you're going to place a very large, close to 50% chance on Monday, I suppose, on day one, I suppose.
Yeah, well, but that's entirely driven by the one half of the coin flip, or not almost entirely driven by that.
Right. All right. So here's my formulation that makes the problem a little more interesting. That I think goes to the heart of why it's interesting. So I'm going to change the problem a little bit. I write it this way: God, or appropriately powerful being, flips a coin to determine which type of world to create. A world of population 100, that's world A, or a world of population 10 billion, that's world B. Okay, so he flips the coin, created the world that the coin said, then you are born. Lucky you. What is the probability that you are in world A versus world B?
With no other information beyond these are the two possibilities, and
Right.
you know the fact that you have been born.
Right. So a halfer would say 1/2. But I think a thirder might say, well, I'm much more likely to be on world B because world B has a much greater population. So
Right.
there's if I'm picking an average consciousness, I would be on world B. Now I'm going to change this a little bit.
Well, is there a nuance there in the question of, does the coin get rolled, or the coin get rolled? Does the coin get flipped to determine the creation of the worlds, or does the coin get flipped every time somebody is born?
No. Only the beginning to
Okay, so
decide what world.
so that drives me much stronger towards the halfer point of view.
Right. Now, I think one of the problems here is there's no information given as to the probability of which consciousness you're going to inhabit. So that's that is kind of a puzzle there. And so I think this is related to the problem of the prior. Okay. Now we have another one. Suppose God creates both worlds A, world B, decides, you know what? Who am I to play dice? I don't play dice. Maybe God, maybe to use the third person, God does not play dice. You know, I picture that. So we've got world A and world B both created. And
It's the Oprah approach. You get a world, and you get a world,
you get a world,
and you get a world.
So one world has 100 people, another one has 10 billion. You are born. What's your probability on the 100 world, and what's your probability on the 10 billion world?
So I want to be intellectually consistent and say, well, why would that change me from being a halfer? But that feels wrong.
Right. It feels like you should inhabit a random consciousness, in which case you're far more likely to be on the 10 billion world. But then we have a question, because this did happen. We have been born. And so does that mean we are way more likely to be on a high population world, or the only world, if there is no extra life in the universe? Why are we not what is a species that is way more common than the human being?
Ants.
Ants. Why are we not ants? Like, you know what I mean? Like, did we just win some astronomically impossible lottery and become humans.
Well, this harkens to, and I don't know if it was actually something that Sagan said in Cosmos, but something very, very Cosmos-y sounding that, given the probability of every physical process in the universe and the odds that your great grandparents were born and had their children and their children, their children, their children, and eventually that you were born is so infinitesimally small. But the counter argument to that would be that, but I was born. So the odds of that happening are 100%.
Or 100%. But then there's the question of, given that I was born, was there, is it like, it seems like, okay, this world should be a more common world and other worlds should be less common. You know what I mean? Like we should be in a very common situation probabilistically. We should not be in a very uncommon situation. So that's one way cosmologists kind of look at the universe, where it's like, well, I'm kind of a random observer of the universe. So given that I'm an observer, given that I have the opportunity to observe, I'm kind of I should be a common case. That's one of the reasons why they say the world could end, in soon, because we are, somehow, like, if you count the number, if you're like human being number X, then you could estimate by like Lindy's law or something, the world ends around 2X. And
the second half is going to pass a lot faster than the first half, because maybe not logarithmic or exponential, but we're not growing linearly.
Yeah. No, I don't quite buy that. But I do think there is kind of an open question about what constitutes a consciousness. Like, if someone has multiple personalities, then do they get extra probability for each personality? If you're a swarm of bees, do they each get one chance? So there's kind of a problem with, there's kind of a problem with this like random observer type question, which I think is very deep. And I think we're going to get some really interesting responses, because I have not thought about this philosophically enough to go deeper into it. But localmaxradio@gmail.com or maximum.locals.com to chime in. Any other thoughts on this? Because I feel like I could be pushed on this and pushed into a corner for what I just said.
So not on this specifically, but the talk of God or a appropriately powerful being, doing a coin flip, it made me think of another kind of decision theory scenario. I think it's called Newcomb's problem, involving two different boxes and a all-knowing being named Omega, which we don't have time to get into today, but might be worth discussing in a future episode.
Yeah. All right. So we have a reader submitted question, which is kind of interesting. I think we can get through this very fast, and then probability distribution of the week. So we're ready to start the reader question.
Yeah, lay it on me.
All right. This is a reader submitted question about Major League Baseball. Max, love the show. Thank you for all the years of hard work. Yes. I think I found a pattern between Major League Baseball playoffs and the Monty Hall problem. I wanted to know what you thought about it. MLB wants to have more teams in the playoff, but the higher seeded teams to win more often. To make this happen, they have a first round that the lower seeded teams play in, and the top teams get a bye and don't play. Based on the following premises, the playoff system results in the lower seed winning more often. So I without reading the rest of it, I think we can give kind of a summary of what's happening, because I have not been following baseball for ages, and I didn't know about this. So it used to be that each division had 4 teams in the playoffs, but the 4th team was known as the wild card. And so 2 teams would kind of face off for that wild card. Now I believe they have essentially 2 wild cards. So in other words, you're doing like March Madness style in the second round, where it's 1 plays 4 and 2 plays 3.
Okay.
But essentially the 3 is gotten because there's a pre-round where 3 plays 6, and the 4 is gotten on a pre-round where 4 plays 5. So essentially the top 2 teams will get a bye in the first round. And I think which they sort of did in the previous version, but that was really just the week that the 4th and 5th
ranked teams played for that wild card slot.
Right. That wild card was kind of like a bye for everyone else, wasn't it?
Yeah.
So I think the argument here is that, well, first of all, baseball is one of those games where the differences in the teams are not as large as in other sports. So you'll have, winning teams. I don't even know what the average numbers are. I don't know my baseball stats, but it might be like 55-45 wins to losses versus like, in other sports, there might be like 70-30 or something, or even in football.
So among the top tier, the variance is much smaller.
Right. So I think what he's arguing is that, look, there's going to be a certain team that's going to be the winner. But now that you've gotten to bye the first round, let's say you're a high-seeded team, now you're playing the winner of two lower-seeded teams. So you're less likely to be the best team among those three than you are to be the best team among you and a random choice of one of those two. So I think he's saying that the highest seeded teams will be more likely to lose. But I don't think it is true that it's going to be like one of the assumptions that he's giving here is that, well, if they're all 33% chance of being the best team, then now you've gone from a 50% chance of winning down to a 33% chance winning, essentially. But I think if you're seated higher, there must be some value that it must be some larger
right.
value.
So there's a assumption or an assertion being made that among the three teams in any branch of the playoff bracket, they are equally likely to win either in a matchup or in the overall branch of the bracket, which you're taking issue with. That yes, they may all be closely ranked in terms of statistical performance and capability, but not sufficiently close to give it an even
right
1/3 breakdown.
So he has observed that lower seeded teams are winning a lot this year, and so that could be part of it. I mean, I don't know how you'd test it. You might need more data in order to do it, and I certainly don't have the. I'm certainly not going to do the data analysis.
It's tough to
get those probabilities.
Abstract out what is chance this iteration versus what the underlying statistical likelihoods would be. Because I mean, you could run those scenarios multiple times, but I think a large part of that is resting on some of your fundamental assumptions, like whether are you assigning a 1/3 probability of victory to each of these teams before you go and run that through however many games are in a series for each round of the tournament.
I wonder if you can somehow use past data. Not that I'm going to do it, but if you could somehow use past data to sort of look at how you're seated and then use that to come up with a probability of your likelihood of winning. You kind of assume that the seed is some probabilistic value on the score that you'll ultimately get, and then everyone's kind of ranked by score in terms of whether they win or not. It's really a vast oversimplification. I think it's an interesting model, though. I think there's something to it. I think it's very difficult to.
Did you already talk about the potential link to Monty Hall?
That was in the email.
But,
I think the relationship to the Monty Hall problem, I think that the idea is that in the Monty Hall problem, you closed one of the doors, and then the probability of that door gets transferred into the other door that you didn't pick. And so that's the idea. They picked the one seed in that round, the one with the bye. That's the one they think is the winner. And then there are two teams playing, and then essentially the team that win is closing the door on the other team as to who the best team is. And I think what he's saying here is that if the probabilities are close to a third, but even if they're not a third, you've just decreased the chance of the one seed from winning.
Yeah, if you deviate from this even 1/3 distribution of likelihood to win within that branch of the playoffs, if you reallocate it so that it's 50% to the one seed and 25 to the wild card contenders, it still means that they're coming out of that now as a 50-50. which is much stronger than one of the teams went into it.
Another way of thinking about it, you're essentially just adding the probability. They're just adding a 6 team, team 6.
Yep.
You're essentially adding the probability that team 6 is really good and it's going to beat everyone, which honestly might not be that high. Although in baseball, it might be.
Well, and our listener has said that the objective of Major League Baseball here was to build a system where the top seeded teams win more often, which I'm curious whether that is more or less attractive from a viewer perspective. That like I know in March Madness when there's a round one upset where and which I think rarely ever happens, but if a 16 seed beats a 1 seed, like that's a big deal, and it's presumably it's got to be a pretty epic game to watch, which would be great for viewership.
Yeah,
maybe that dynamic
in the NBA sometimes.
Maybe that dynamic doesn't work when you're playing a best of 3 or best of 5 or best of 7 series, but maybe it does. I mean, that's the other thing is that we didn't read carefully enough on this to see if any of these are sudden death. Or if these are all series games, is the wild card round, a single game, or is it a 3 or a 5 game series? And the longer the series, presumably, the less likely you are to have an anomalous upset. That's going to tend to be weighted in favor of the team that is actually statistically superior.
Yes. All right. So now, are you ready to have your mind that was pretty mind blowing. You ready to have your mind blown a third time?
I don't know how much I can take in a single episode.
That is right. The probability distribution of the week. And because we have such a crazy episode, I figured I'd pick a crazy distribution. What do you think? One that doesn't come up that much. And that is called the Zeta distribution, Z-E-T-A. Have you heard of that before?
I've heard of a zeta function.
It's related.
But don't ask me to explain what the zeta function is.
Okay.
Is zeta is it a Greek letter?
Yes,
okay.
I believe it's the letter Z. If I had to take a guess,
but it's not the last letter of the Greek alphabet, because that would presumably be omega, right?
Oh crap! You're right. Well, no, wouldn't that be in the G position because G and Z were switched? I'm not going to look.
You've
this
exhausted my knowledge of the Greek alphabet.
Yeah. Okay. So let's look at it this way. Last week, a couple weeks ago, there was a solo show, but I did Zipf's law. I don't know if you remember that, but that's the law where it's like, okay, the most likely word, if that's at 1, the next word is going to be half that probability in terms of just the probability of any word. Imagine like a huge categorical distribution with all the words in English. Same with letters. Like if the first letter is at a frequency of 1, unnormalized. The next one is at 1/2. The next one is at 1/3. The next one is at 1/4.
And this is just talking about the corpus as a whole. We're not necessarily looking at, like, given a word, what's the likelihood of a particular word following it?
No, that's bigrams.
Right.
And now you're getting into natural language processing. No, I'm just talking about turning that into a simple categorical distribution.
Okay.
And every language follows some kind of Zipf law, which is really interesting. And even Esperanto, so it's like, it's almost something where it would be very difficult to design a language and in a corpus that does not follow this pattern.
I am by no means a linguist, but I want to reach out there and grasp at some sort of language that is sufficiently anomalous in the way it's constructed, but I can't think of it.
Yeah. So now an issue comes up when you want to make this distribution infinite, because let's say you want to be able to create an infinite number of words or something like that. Now, so you have 1, 1/2, 1/3, 1/4, 1/5. Now, when we stopped before in Zipf's law, let's say there are 30,000 words, 100,000 words. We could add up all those numbers and then divide by that, and that is your normalization constant, and you have a probability distribution. I'm going to quiz you on calculus from 20 years ago and see if you know what's the problem if I try to make this into an infinite distribution.
I assume that it doesn't converge.
Yeah, exactly. So it goes off to infinity.
That's always the answer when something is difficult in calculus.
Yeah. So that's called the harmonic sequence, and it does go off to infinity. But what mathematicians can do is they can put an exponent in the denominator. Because why not?
Before you go on, does harmonic is that directly related to like harmonics in the acoustical sense?
Actually, it is. Yeah. Because in terms of, I don't know exactly, but in terms of like how the different waves line up, they're all fractions of each other.
Well, yeah, because isn't it like an octave is basically half the frequency or something?
Yeah. So half, a third, a fourth, a fifth, and those are called harmonic. I think, I'm not sure if the math came from the music or the music came from the math, but it is related. Essentially, think of it as just a large piece of music.
An infinite piano.
Yeah, an infinite piano. All right, so you put a little exponent in the denominator. Now, that exponent could be close to 1, which is interesting enough. So there's another problem called the Basel problem, which is 1 over 1 squared, which is 1, 1 over 2 squared, which is 1/4, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, et cetera, et cetera, et cetera.
So this is Basel, not Basil?
Maybe it's Basel. I don't know. Anyway, that converges to like 6 over pi squared. So obviously, who could possibly? So that the normalization constant is pi squared over 6 for that, or if you prefer, tau squared over 24, tau squared over 4 factorial.
Tau does not give me hunger pangs the way pi does.
No. Okay, so that converges. Now you could actually make that exponent very close to 1, and it still converges. So you could be like 1 over 1 to the 1.01, 1 over 2 to the 1.
But if you make it 1, it goes to infinity.
Right.
So it just needs a tiny nudge.
It needs a tiny nudge. And so you could make a distribution out of that because that is also that converges. And you could still try to analyze language in that way. You can say, hey, I'm going to assume this language has an infinite number of words, even though it doesn't, because sometimes when you use infinity, actually in math, infinity sounds really hard. But sometimes infinity, things work out nicer than if you do really, really large. And sometimes these little exponents actually, like you could try to estimate what the exponent is for each language, and maybe some of them are so close to 1 you can't do it. Maybe some of them are 1.02, and so they all have kind of a little exponent that you can learn. And different languages have different exponents. Or different schemes have different exponents. So that's very interesting.
Is the way we would determine that is literally to take the empirical evidence and try and kind of fit the curve?
For languages, yes, and for other similar things. There's also a similar thing is like the distribution of species also follows a Zipf's law kind of a thing, and or the infinite.
When you say distribution of species, you mean like how many ants there are compared to whatever the next most common organism? Okay.
Yes. Yeah. And maybe other areas in nature will come up with this. Now, the interesting thing is, remember I said that exponent, so long as it's a little bit bigger than 1, it converges. Now, you could make a function out of this. So given the exponent, what does it converge to?
I'm afraid to ask because this is going in a different direction, but what if I make it less than 1?
If you make it less than 1, so let's say then it diverges.
Okay.
Because you're actually...
not only does it diverges horribly.
Yeah, like you're making it... so if it's 0, you basically have 1 plus 1 plus 1 plus 1 plus 1. If you make it -1, you have 1 plus 2 plus 3 plus 4 plus 5. And that sum goes off to infinity and then arrives at -1/12, obviously. So, but we'll get to that in a second. So you think, okay, why don't I graph that? Like, where does it converge? Even though like some of these like convergence points they're mostly like horrible, irrational numbers, and the pi squared over 6 or 6 over pi squared. I don't remember I'm sure I could figure it out, but it's like, how did they get that? It's actually a really cool proof. But you could estimate almost all of them, just by computationally. So you could graph it, and it kind of just looks like a curve that's kind of comes from a asymptotic point at 1 and sort of goes down. So it's like, given the exponent, what does it converge to? Obviously, if the exponent is infinite, then it just converges to 1 because it's,
Yep.
yeah. So the all the other terms except for 1 go to 0. So it's kind of makes this U shape, and that is actually known as the Riemann zeta function. And so that's why it's called the zeta distribution. Zeta function is really important in pure mathematics. And in fact, so that function is infinity at 1, but it does take on values less than 1. And so that's why there's kind of an iffy if it, and at -1, it takes on the value -1/2. That's -1/12. And that's why I said that before.
Is Riemann zeta somehow involved with encryption, or am I crossing my wires here?
I'm not sure if it's involved with encryption, but it's involved with prime numbers. So I wouldn't be surprised.
It's definitely something I've seen before, but it's a piece of my brain that I haven't used in many years.
Yeah. So it is definitely it's involved with the Riemann hypothesis, which again we could do a whole show on that.
Was that one of those unsolved? Is it still unsolved?
Yes.
Okay.
And
it has a prize associated with it?
Yeah. It's a big one. It's one of those ones where mathematicians look at it and they're like, this might not even be decidable.
But if you were to solve it, then that would be, maybe not Nobel Prize worthy, but it would be a crowning moment of your career.
It would be $1 million, which sounds like a lot of money, but given my there's a way easier ways to make $1 million. Now, if it were $1 billion, maybe, but so many people can make $1 million.
Well, and I don't think this is the direction we were planning on going, but presumably that there is a value to solving it beyond just the pure joy of academic pursuits. Is there a way that a solution to that hypothesis could be monetized?
Yeah, no, it's a little bit outside the scope. So I don't know if it could be monetized, but certainly I know that there are a lot of theorems in mathematics, like a lot of them that depend on the Riemann hypothesis. So you get a lot for that one
Gotcha.
That one thing. And it does seem to be some kind of a very
so would a solution
profound statement about the
break
distribution of prime numbers.
those processes, or would it just put them on a much firmer foundation?
Firmer foundation.
Gotcha.
Yeah. Or to prove the hypothesis, which is actually that something doesn't exist, zeros don't exist. The complex plane of the zeta function.
This sounds like it could require an entire show to dig into.
Way more. And also, why does this thing have anything to do with prime numbers? That's also really weird. But this is actually a good distribution for a lot of theoretical problems that come up, I found. And it's actually a lot more interesting of a distribution than the geometric distribution, which, that's the one that goes 1, 1/2, 1/4. And that one, the problem
which you would think would be pretty similar.
They're similar, but this one has a much fatter tail. Even if you put a 99% in terms of from the first one to the second one in terms of the geometric distribution. In other words, it shrinks very small. At some point, it gets very tiny, and all of your everything you draw from that distribution is kind of low. Whereas this distribution, if you draw from it, if you have an exponent that's close to 1, you could end up with some really high numbers, things really out in left field. So it's a really high-tailed function, which makes it kind of interesting. There are other ways to do fat-tailed functions, or distributions, but this is one of them. And I think that's the reason why languages and ecologies use this, because if they used a geometric distribution, you wouldn't have that much diversity. It would kind of fall off after a while, and you wouldn't have that kind of long tail of plants or words or whatever you're looking for. And so yeah, really fascinating one. Zeta, it doesn't come up a lot in practical stuff, like when you're doing marketing data and stuff, but it does come up in Nature, and it is really interesting for theoretical purposes. So, all right, I think that wraps up the show for today, unless you have another question about Zeta.
No, I was just saying, it's always neat to see something that pops up in mathematics that is derived from not just the real world, but the natural world.
Yeah. And then it's nature.
Golden ratio and that type of stuff.
And then it has this connection to pure mathematics and cryptography, which is or prime numbers, which is just so mind-blowing. So that's really cool. All right. Next week, Well, I don't know. I might do a solo show because I'm traveling a little bit. I might be talking about the debate. I might be talking about the election coming up. I know we've talked about the election the last 2 times, and I don't know what else I could say about predicting the election, but maybe I'll think of something to say about it. And yeah, that's it. Rounding out the end of the year. Beautiful this time of year in New Hampshire. I drove through Exeter today, and it's just like a picture-perfect fall day in New Hampshire. So for those of you in the Northeast, hope you enjoy this week and this kind of perfect weather. For those of you rest of the country, come visit. Have a great week, everyone. That's the show. To support the Local Maximum, sign up for exclusive content and our online community at maximum.locals.com. The Local Maximum is available wherever podcasts are found. If you want to keep up, remember to subscribe on your podcast app. Also, check out the website with show notes and additional materials at localmaxradio.com. If you want to contact me, the host, send an email to localmaxradio@gmail.com. Have a great week.
Feel the power.